Welcome to today's intriguing journey into Plato's allegory. This allegory serves as a fascinating gateway into the questions that mathematicians began to grapple with in the 18th and 19th centuries, questioning the very foundations of mathematics. As Plato did, imagine a group of people reasoning about the real world, much like prisoners in a cave. They see only the shadows of real things projected onto a wall. These shadows, they believe, are the reality. However, what if these shadows are just an imperfect picture of the reality outside the cave, a reality they can never really understand? This is the essence of Plato's allegory, a concept that profoundly impacts our understanding of mathematics. Plato's allegory captivated the imagination and laid the groundwork for a significant philosophical orientation in mathematics, Platonism. Platonists, including many famous mathematicians, believe in the possibility of building mathematics on abstract concepts. These concepts, they argue, do not necessarily have to correspond to reality, as long as the resulting theory remains free of contradictions. In one of my previous videos, we explored Euclid's Elements, a work that has shaped the course of mathematics for millennia. The geometry presented in the Elements has been accepted as the bedrock of mathematics until the 19th century. If you say today, no, the foundations of mathematics is set theory or category theory, this was not always the case. Euclidean geometry was the foundations of mathematics for millennia, and it was believed to be the geometry of the real world. Its logical implications, such as the existence of non-intersecting straight lines, we call parallel, and the constant sum of 180 degrees of all three angles in a triangle, were widely accepted as undeniable truths until the 19th century. This slide showcases Euclid's original formulation of how to define parallel lines in his visual proof of the angle sum theorem, which provides visual evidence of the truth of Euclid's axioms. Let us see how Euclid proved this theorem. If you have any triangle ABC, you can draw a line parallel to AB. Let us call it CE. Then you can see that the angles BCA, ACE and ECD equal 180 degrees. And it is clear from that construction that these angles equal all three inner angles of the triangle. For the angle BCA is already an inner angle of it. The angle ACE equals the inner angle CAB, and the angle ECD equals the angle ABC, since the lines BA and CE are parallel. So let us delve into one of Euclid's 5 axioms, the parallel axiom. This hypothesis states that if a straight line intersects two other straight lines in a plane in such a way that the internal angles on the same side are less than two right angles, 180 degrees, they will eventually meet on that side if produced to infinity. This hypothesis, with its rich history and controversy, has been a subject of fascination for centuries. Until the 19th century, mathematicians believed in the truth of the axiom, but they endeavored to eliminate it, attempting to prove it from the remaining four axioms. Euclidean geometry, long upheld as the foundation of mathematics and a fundamental aspect of reality, encountered its first major hurdles in the 19th century. Renowned mathematicians, including Carl Friedrich Gauss, began to question its universal applicability. Gauss, for instance, noted that the sum of a triangle drawn on the surface of the Earth often surpasses 180 degrees, a phenomenon that contradicted Euclidean principles. This marked the initiation of the exploration of non-Euclidean geometries, a significant turning point in the history of mathematics. Gauss was entrusted with the systematic land surveying and topographic measurement of the Hanoverian Kingdom, today part of Germany. During his measurements, he used light signals to measure the angles in a massive plane triangle formed by three German mountains. Some sources suggest that Gauss just aimed to obtain a control measurement for some smaller measurements. Other sources speculate that Gauss used this opportunity to provide physical evidence that the parallel axiom was flawed. After his measurement, Gauss realized that within the allowed measurement error, the angles in the great triangle indeed added up to 180 degrees. So his intention to disprove the parallel axiom, if he indeed had this intention, was not successful. Regardless, Gauss's actions marked a significant step in questioning the parallel axiom's validity. And remember, questioning the parallel axiom meant questioning the foundations of mathematics, since until 19th century, Euclidean geometry was considered the bedrock of mathematics. In the following slides, I will provide you with many examples of first doubts in the foundations of mathematics emerging between the 17th and the 19th century. As it comes to non-Euclidean geometries, two mathematicians, the Hungarian János Bolyai and the Russian Nikolai Lobachevsky, published works independently of each other about new geometry types defying the parallel axiom. In these geometries, the sum of angles in every triangle is greater than 180 degrees. So, how could space be both Euclidean and non-Euclidean? Remember what we said about Boolean logic in my previous video? In Boolean logic, some expressions are true under any interpretation. We call them tautologies. And you get a contradiction under any interpretation if you negate a tautology. If you imagine a formal language in which we somehow succeeded to express the parallel axiom in a way that is always true under any interpretation, how is it then possible that we could, on the one hand, base geometry and mathematics that is free of contradictions on Euclid's 5 axioms, including the parallel axiom, and on the other hand, negate one of Euclid's axioms to create again a geometry that is free of contradictions? To pick contradictions arising in physics at this time period, let us take Thomas Young as an example. He performed in 1800 an experiment showing the interference pattern caused by light passing through two slits. It proved the wave nature of light, which contradicted what Newton took for granted, stating that light consisted of particles. Other renowned physicists, including Hertz and Maxwell, confirmed the wave nature of light. However, between 1877 and 1905, new experiments with photocurrent revealed that it depends on the frequency of light rather than its intensity. This evidence contradicted the previous conclusion and suggested again that some particles, not a continuous wave, transport light energy. This result later became known as the photoelectric effect, an explanation of which later brought Albert Einstein the Nobel Prize. Even though modern physicists consider the particle-wave dualism of light, it still remains a deep mystery to them. From the 17th to the 19th centuries, mathematicians were baffled by increasing curiosities and apparent contradictions. Some mathematicians doubted, for instance, the equation +1 divided by -1 equals -1 divided by +1, since they wondered how we could get the same result if one divided a smaller measure by a greater one and vice versa. Other curiosities of this kind occurred when handling some infinite sums. How could we get different results by bracing the same infinite sum differently? In the 18th century, a function was understood as a single analytical expression. So if the logarithm was a function, a distinction of cases like the one shown here had simply to be ruled out. Thus, mathematicians struggled with functions that couldn't be written down as in a single analytical expression. However, Jean-Baptiste Fourier's ingenious suggestion was that curiosities for which the mathematicians struggled with finding a single analytical expression, such as the sawtooth wave, could be understood as functions being the limit of some special infinite sums of analytical expressions. His infinite sums were composed of continuous functions, each expressible by a single analytical formula. Still, they converged to things like the sawtooth wave, which is neither expressible by a single analytical formula, nor a continuous function. This paradoxical phenomenon piqued the curiosity of many mathematicians. How was that possible? Gustav Dirichlet introduced a truly unique function that defied even Fourier's approach. Dirichlet's badly behaved function equals 1 for all rational numbers on the number line and 0 for all irrational numbers on the number line. It was already known that rational numbers lie densely in the number line, meaning there are infinitely many rational numbers in every, even the smallest interval of the number line. Dirichlet's function with its peculiar properties is so pathological that there is no value of x for which it is continuous. Neither is it expressible by a single analytical formula. I began this video by delving into Plato's allegory. Now, as we draw to a close, I want to emphasize the profound impact of the spirit of doubt on the omnipotence of science and the limits of scientific insight. The philosopher Immanuel Kant, in his Critique of Pure Reason, argued that the representation of a body is merely a phenomenal appearance of something. Even if we would see to the very bottom of a phenomenon, it would remain forever altogether different from the knowledge of the thing itself. Émile Dubois-Reymond, a pioneer in electrophysiology, who conducted groundbreaking experiments on nerve potential in human bodies, was invited to the Congress of German Scientists and Physicians in 1872 to deliver a keynote. His keynote, titled "About the Limits of Our Knowledge of Nature," left us with a profound sense of the unknown. He concluded with the Latin phrase ignoramus et ignorabimus. We don't know, and we will never know. The conclusion, ignoramus et ignorabimus, sparked a heated and ongoing debate among 19th century and 20th century scientists and mathematicians. This controversy revolved around whether human intellectual insight can fully understand natural phenomena or is fundamentally limited. We will delve deeper into this intriguing dispute in a future video. Thank you for joining me on this journey, and until next time, goodbye.